Hello, everyone. Today we'll go over the question from the practice exam 2. And for this practice exam, the grade already available this morning. So you should be able to go back and then check your grade and also the question you missed on this practice exam. So let's start with the first question here. Given the function of two variables, which of the following is correct? The first one is asking the domain. So since the function given here is a fraction, so the function is defined whenever the denominator doesn't equal to 0. So we want 4 minus 2x squared minus y squared doesn't equal to 0. So that means 4 doesn't equal to 2x squared plus y squared. Okay, so the domain part is correct. All right, so this is the first one. The second one is asking the range, and the third one is asking the level curves. The range is a little bit harder, so let's do the level curve first, okay? Because sometimes the level curve and the range is kind of related, okay? So to determine the level curve, we're going to set the function equal to a constant, let's say k. Set the function equal to k value, and this k is in the range of the function. Okay, k is a value in the range. Now we want to determine what's the level curves. So let's determine what's the equation for x and the y here. Okay, so first of all, let's take the reciprocal on both sides here. So we get 4 minus 2x squared minus y squared equal to 1 over k. Okay, and we're going to move the x and the y squared to one side here. So we have 2x squared plus y squared equal to 4 minus 1 over k. Okay, so we have 2x squared plus y squared equal to a number. So what's the level curve do we have here? The sum of 2 squared. So do we have ellipses? Yes. All right, so R is correct here. Okay, so the level curve we have here, this those present ellipses. Okay. And now we're going to use this concept from the level curve here to determine the range. Remember, we mentioned that the k value is in the range of f. And this presents an ellipse. 2x squared plus y squared equal to a positive number that present an ellipse here. So that means the sum of 2 squared, we want this is always greater or equal to 0. If it's less than 0, then there's no level curve. Okay, so we want the sum of 2x squared and the y squared is greater or equal to 0. And we can solve for k here. Once we solve for k, that gives us the range of the function. Okay, so we have 4 minus 1 over k is greater or equal to 0. To solve the inequality here, we can find the least common denominator. Okay, so we have 4k minus 1 over k is greater or equal to 0. And to solve this inequality, we can set the top and bottom equal to 0 to find the critical point. Okay, so you're going to get 0 from the denominator and 1/4 from the numerator. And we have 3 intervals here, 3 test intervals. Okay, and you can test the interval. For example, for the interval from 1/4 to infinity, you can pick something bigger than 1/4. Let's say k equal 1. When you plug in k equal 1 into this fraction, you have positive over positive. So the entire whole thing is positive here. Okay, and you can do the same thing for the other 2 test intervals. Okay, so you're going to get the sign for the test intervals are starting from the left, you have plus sign, minus sign, plus sign here. Okay, and we want the fraction is greater or equal to 0, so we want to have a positive intervals. Okay, so that means the k value will fall into those 2 intervals here. And so k is from minus infinity to 0. Should we include 0 here? We want the inequality is greater or equal to 0, but you can see k is in the denominator, so that means k cannot be 0. So it's open interval here. And then from 1/4 to infinity, should we include 1/4? 1/4, when k equal 1/4, we have equal to 0, that's fine. The numerator can be 0, so we include the 1/4, okay? And so this is the solution for the k value, and the k value is in the range. So therefore, this gives us the range of the function, okay? The range is from minus infinity to 0 and 1/4 to infinity. So if you look at the Q statement, the statement Q here, it says the range is from 0 to infinity. This one is not correct, okay? It should be from minus infinity to 0 and then 1/4 to infinity. Okay, that should be the range of the function. So this is the first question. And any question for the first one? All right, let's move on to the second one here. The second question, it gives us a piecewise defined function. When x comma y doesn't equal to, it should be 0, 0 here. Okay. And when x comma y equal to the origin, we have the function value equal to 0. First, it asks us to find the limit here. We want to find the limit when x comma y getting close to 0, 0. So to find the limit, we're going to plug in the tangent function, tangent x squared y over x to the power 4 plus y squared. Okay, when we plug in 0, 0, we got 0 over 0 here. So can you tell me how we're going to find the limit when we have a 0 over 0? Okay, so when we have a 0 over 0, okay, can we do the L'Hopital's rule? Can we do the L'Hopital?
Not on a function of two variables.
No, that's correct. When the function, the L'Hopital's rule only works for the indeterminate quotient when we only have one variable. When we have two variables, we cannot do the L'Hopital's rule, okay? And we'll see if we can simplify, okay? So like if you can factor out like a common factor, you can simplify. For this one, there's nothing we can simplify here, and it doesn't involve the square root, so we cannot multiply the conjugate. And it doesn't involve the x squared plus y squared term. If it involves the x squared plus y squared term, you can convert to the polar coordinate. So now we are out of choices here. We cannot simplify, we cannot multiply the conjugate, we cannot convert to the polar coordinate. Then what else can we do?
Test the limit from different sides and see if the limit exists.
So as you can see, it looks like we are out of choices here, okay? So we might consider the limit for this function probably does not exist. So we are going to consider like two different paths here, okay? So let's consider along the path x equals 0, for example. So we'll have tangent 0 over 0 plus y to the power 2, and y goes to 0. And tangent 0 is exactly 0 here, okay? So 0 over y squared give us 0, okay? So along the first path, we got the limit 0. And now since we want to show that the limit does not exist, so we want to choose another path. And I saw some path on on the chat here. So if you choose like a y equals 0, y equal x, okay, now yes, Nick, he mentioned that y equal x squared. So we want to choose y equal x squared. The reason is you can, when you have a sine or tangent, you can kind of ignore that tangent for now. And you want to pick a path so that the top and bottom has the same degree. So the path we're going to choose here, y equal to x squared, okay? So we'll have, replace the y with x squared. So you'll have x squared times x squared on the top. And the denominator is x to the power 4 plus y squared is also x to the power 4. Now we let x go to 0, okay? So here we are going to get tangent x to the power 4 over 2x to the power 4. Now when x goes to 0, you can see we have a 0 over 0 here. So if you want to use the L'Hopital's rule here, that's fine because now we only have one variable, okay? When we have one variable, we can do that, okay? So if you want to use the L'Hopital's rule, you can do that here. The derivative for tangent is secant squared. Chain rule, go inside, take the derivative for x to the power 4, you got 4x cubed. Divided by the derivative for the denominator, you're going to get ax cubed, okay? So now you can cancel the x cubed. You can cancel factor of 4, so that left with 2 in the denominator here, okay? So when x goes to 0, secant 0 is 1, so we have 1/2 here. So along the path y equal to x squared, we got the limit 1/2. And this limit is different than the limit we got earlier along the path x equals 0. So you can see this along one path, we got x, the limit is 0. Along y equal x squared, we got the limit is 1/2. Therefore, you can see since these two limits are different than each other here, therefore the limit does not exist. Okay, so P is not correct. The limit does not exist here, okay? Because along two paths here, we got two different limits. Therefore, the limit does not exist. If the limit does not exist, then of course, it doesn't equal to the function value, right? The function value is defined as 0 here, okay? The function value at the origin is defined as 0. So the limit doesn't equal to the function value. Therefore, the function is it continuous? It's not continuous, right? When we have the continuity, the limit value has to be equal to the function value. Okay, so Q is not correct. F is not continuous. So if the function is not continuous, then how can we say about the differentiability? The function is
Function's not continuous, then it's not differentiable.
Yeah, so R is correct here. So only R is correct. Okay, only R is correct here. Is that good?
Yeah, before you go on, I had a question. So you said there were 4 different choices for solving these limits. Could you repeat them? I remember you saying simplify and polar and test different paths.
Yes, so you're going to simplify. So that means if you're going to see if there's a common factor, you're going to do the factoring. Okay. And if we cannot simplify, you're going to see if it involves the square root. If it involves the square root, you're going to multiply the conjugate. Okay, you multiply the conjugate and then simplify. And if it doesn't involve the square root, then you're going to think about if the fraction we have here involves the term x squared plus y squared. If it involves the term x squared plus y squared, then you're going to convert to the polar coordinate. So if now this work, then this will be the last choice. You're going to consider 2 different paths if the limit does not exist. Is that clear?
Yeah, it is. Thank you.
All right. So this is question number 2. Any question before we move on?
Oh yeah, I have a. Oh no, go ahead. You're good.
Okay, sorry. Could you also have solved this by doing, if you plug in y equals x squared, the argument of tangent is the same as the denominator, and that's 1.
You plug in what?
So the same thing as how we did y equals x squared, but then I just simplified it by the rule that if like the argument of tangent is the same as the denominator, then it's 1. So then I just had 1/2.
So I guess you are using this limit here. Tangent theta over theta equals to 1. Are you?
Yes.
Yeah. So if you don't want to use the L'Hopital's rule and you remember this from Calc 1, yes, you can use that.
Okay,
If the top and bottom has the same angle and now the angle goes to 0, this goes to 1. This also works for the sine function, sine theta over theta. That also works. Okay.
Thank you.
Oh, I have one quick question on this.
Yes.
So let's say it were continuous. How would we go about proving it's differentiable at 0, 0?
Okay, the differentiability is not that easy to prove. In the lecture, we mentioned that in order to have the function differentiable, you need to have two conditions. One is both partial derivative exist at the given point, okay? And second, both of them are continuous. So if you have both of them, then we'll say the function is differentiable, okay?
Okay, but the partial derivatives are continuous, right?
Yeah, the
Okay,
partial
all right,
derivative are continuous
all right,
near
thank
the
you.
point, okay? You need to have both of them. That will guarantee the differentiability, okay? And this is one of the theorem we mentioned in the lecture. You can go back to check the lecture notes, okay? All right.
All right, that
Now,
makes sense, thank you.
And let's move on to question number 3. We want to determine the set of all points at which the function is continuous. And because the function we have here, both of them are the square root function. And from Calc 1, we know the square root function is continuous on its domain. So basically, to find the set where the function is continuous is the same thing as to find the domain here, to find the domain of the function. Because this is a square root function, so we can do that, find the domain of f. So to find the domain is not that bad at all, okay? Because we have two square root function here. So we know everything inside the square root has to be greater or equal to 0. So the domain is y is greater or equal to 0. And also the second one is inside the square root has to be greater or equal to 0. It satisfies both of them, okay? And the second one here, we can rewrite this as x squared plus y squared is less than or equal to 1. So as you can see, this present a unit disk. X squared plus y squared is less than or equal to 1, a unit disk, okay? However, we don't consider the entire unit disk because we also need to satisfy y is greater or equal to 0. So that means we only consider the top half, only y is positive, okay? Only the top half of the unit disk here, okay? So which of the following present the top half of the unit disk? If you look at the first one, from the minus square root to positive square root, that's the entire disk. And for this one, so for the third, of course, it's not the second one here. There's a restriction on the xy, okay? How about the third one? What does the third one present here? X is a positive and is less than or equal to 1 square root of 1 minus y squared. So that presents the right side of the disk. Can you see that? When x is greater or equal to 0. Okay, so that one is not correct. And the fourth one, x squared plus y squared equal to 1. So that's not a disk, it's just a circle. Only the boundary here, okay? So that's not the answer. And the last one, y is greater or equal to 0, so this is good, okay? And it's less than or equal to square root of 1 minus x squared, so the last one is correct here. So that this and the last one, it gives us the domain of the function, okay? And let's move on to question number 4. We want to find the second partial derivative here when the function is given. So let's find the partial derivative with respect to x first. We have xy times the log function. Therefore, we need to use the product rule here. Xy is one function, log is another function. So the product rule, take the derivative with respect to x. So we have y here times log, the ln, plus xy times the ln function. The derivative for the ln function is 1 over 2x squared times y. And go up, go inside here, we're going to take the derivative, chain rule, take the derivative with respect to x. So we have 4xy. So the first step here, we use the product rule. Okay, is that good? There's two terms here. The first one, we take the derivative for xy. The second one, we take the derivative for the log function. Okay, now let's simplify a little bit. The second fraction, we can, let me see, we can get rid of y, we can get rid of both x, and then that gives us 2. So After we reduce it, we got 2y here for the second term. Is that good? So this is the partial derivative with respect to x. Now we're going to take the derivative one more time, and this time we're going to take the derivative with respect to y. Take the derivative with respect to y require another product rule here for the first one. Okay, so 1 times ln plus y times the derivative for ln. So it's 1 over 2x squared times y. And this time when we go inside, take the derivative, we take the derivative with respect to y. So we got 2x squared. Okay, so that's another product rule here. Plus the derivative for 2y, we got 2. Okay, so now we can simplify a little bit before we plug in the numbers. Okay, so the second one here, you can see we can cancel the 2x squared, we can cancel the y, so we got just 1 here. Okay, so this is 1. 1 plus 2, that gives us 3. Okay. So now we're going to plug in the function value at 1, 1. Okay, so we're going to plug in x equal 1, y equal 1 here. So when we plug in 1, 1, we are going to get natural log 2 plus 3. Okay, so natural log 2 plus 3, that's the final answer here for the second mixed partial derivative. Is that good? All right, now let's move on to question number 5. Question number 5, we want to use the linearization of the given function here at the point 1, 1 to estimate this function value, okay? And even though the function here, it looks kind of ugly here, but as you can see on the test, we cannot use a calculator, okay? So we'll try to make the number reasonable for you for calculation, okay? So when we want to use the linearization, so first we need to find the tangent plane, okay? So the tangent plane is z equal to f11 plus the partial derivative with respect to x at 1, 1 times x minus 1 plus the partial derivative with respect to y at the given point times y minus 1. Okay, so this is the tangent plane, and we'll use the tangent plane to do the linear approximation here. Okay, so let's figure out what's the partial derivative with respect to x. The both first partial derivative here. Okay, so the partial derivative with respect to x. What's the derivative for arctangent? Do you remember? What's the derivative for arctangent?
1 over 1 plus x squared.
1 over 1 plus whatever inside the arctangent square. Okay, so that's the derivative for arctangent. And now we're going to go inside, take the derivative with respect to x. So we have y here. Okay, now do the same thing, take the derivative with respect to y. So we have 4 times 1 over 1 plus xy squared. Go inside, take the derivative with respect to y, we have x. Now we're going to evaluate both partial derivative at 1, 1. So plug in 1, 1. Plug in 1, 1 here. So we have 4 divided by 2. So we got 2 here. Same thing, we have 4 divided by 2. So both partial derivative give us 2 here. And what's f11? What happened when we plug in 1, 1 here? So when we plug in x equal 1, y equal 1, we have arctangent 1. So what's arctangent 1?
Pi over 4.
Pi over 4. Pi over 4 times 4, that gives us pi here. So f of 1, 1 is pi. So now we got the tangent plane, which is the linearization. So I'm going to write it this way. We call this is the linearization equal to pi plus 2 times x minus 1 plus 2 times y minus 1. Okay, so this is the linearization, which is the tangent plane. Okay, and when we want to evaluate, we want to estimate this function value here. Then we're going to use the linearization with x equal to 9/8, y equal to 15 over 16 here. Okay, so we're going to plug in the x and the y value into the linearization. Okay, so let's plug in. So we have 9 over 8 minus 1, so we got 1/8 here. Is that good? And plus 2 times y minus 1. So y equal to 15 over 16. When we subtract 1, we're going to get negative 1 over 16. Okay, so even though the number here, the x and y value looks not nice, okay, but once we plug in, it's not that bad, okay? So we'll have pi plus 1/4 minus 1/8, and these two fraction can be combined. You'll find the least common denominator, which is 8. So you have 2 minus 1, that would be pi plus 1/8 here. Okay, so this is how we do the approximation using the tangent plane. Okay, is that good? So this is question number 5. And for question number 6, we want to find the partial derivative with respect to x at the point 1, 2, 3, and given these equations here. So you can see for this equation, x, y, z, they mix together. So we're going to use the implicit differentiation, okay? So let's call this function f of x, y, z equal to 1 over xy plus 1 over yz plus 1 over zx equal to 1. So the partial derivative with respect to x. So if you remember the implicit differentiation, we derived the formula using the chain rule, a tree diagram, we derive the formula for partial z, partial x. Okay, someone already write down the formula for us. That's nice. Okay, so it's negative the partial derivative with respect to x over the partial derivative with respect to z. Okay, so we can use this one here. Okay, all right. So now we can take the partial derivative. So the top, we're going to take the partial derivative with respect to x. With respect to x, so we treat y and z are constant here. So we're going to get -1 over x squared y minus 1 over zx squared. And now we're going to take the partial derivative with respect to z. So we have -1 over yz squared minus 1 over z squared x. Is that good? And once we find the partial derivative, now we're going to plug in the x, y, z value, x equal 1, y equal 2, z equal 3, okay? Now when we plug in, so we'll have the top, when we plug in x equal 1, y equal 2, so we have -1/2 minus, that's minus 3/2, and the denominator, when we plug in 2, and 3, so 9, 18. 1 over 18 minus 9 times 1, 1/9. Okay, and now you just need to simplify here. Okay, we can just simplify. Okay, so because the top and bottom, they both have a minus sign here, so I can just make it all positive here. Okay, because I don't like the minus sign here. So we multiply the whole thing by the top and bottom by a minus sign. Okay, so the top here, when you simplify it, you're going to get the common denominator 6. So you have 3 plus 2, that's 5. And the denominator, you find the least common denominator, which is 18. And you have 1 plus 2, that's 3. Okay, so you'll have -5, 6 times 3 over 18, that's 18 over 3, okay? So you can see 6 times 3, that's 18, cancel with 18 here. So the final answer is -5. Is that good? So the partial derivative at the given point, we got -5 here. Is that good? All right, so on the chat here, someone mentioned that, can we multiply x, y, z on both sides? Yes, if you want to do that, yes. That I think using that way would be easier, okay? So if you multiply both side by x, y, z, I believe you'll get the same thing here, okay? So you're going to get z plus x plus y equal to x, y, z. So now you can let the function to be x plus y plus z minus x, y, z equal to 0. And you can use the same formula. The partial derivative with respect to x is the partial with respect to x over the partial derivative with respect to z. And then you don't need to involve the complex fraction that we did here, okay? So there's two ways to do it. If you simplify the equation first, and then you find the partial derivative, that also works, okay? Is that good? Any question for this one? Number 6? In the chat, it says we have trouble. Someone have trouble with the partial derivative here. When we take the derivative with respect to x, for example, here, when we take the derivative with respect to x, so we have 1 over y times the derivative for 1 over x. So that's the power rule. You're going to get negative 1 over x squared. Okay, the power rule. So that's why we have this one here. Is that good? All right. Okay, so this is question number 6. And question number 7, we want to find the partial derivative when the function is given x to the power 2y. So the partial derivative with respect to x. So we have x to a constant power. Okay, like when you take the derivative for x to the power 10, for example. So how we take the derivative? What's the derivative for x to the power 10? A constant.
10x to the 9th.
So you take down the exponent 2y times x to the power 2y minus 1, the power rule, right? So when you take the power, derivative for x to the power 10th, then you have 10 times x to the power 9. So same thing here. You just treat 2y as a constant here. Take down the exponent, subtract 1 from the exponent. So this is the partial derivative with respect to x. Now take the partial derivative with respect to y. So now we treat y as a variable. Okay, so that means how are you going to take the derivative for example, 2 to the x? Do you remember what's the derivative for 2 to the x? Ln of 2 times the exponential function, right? Okay, so now when we take the derivative with respect to y, so the y, the exponent is a variable, the base is constant. So when we take the derivative for the the exponential function, we need to use this formula here. So we're going to have ln of the base times the exponential function x to the power 2y. And then chain rule, we're going to take the derivative for 2y. So we are going to get 2 here. Okay, so that's the derivative with respect to y. Now we're going to evaluate both of them at the point e comma 2. When we plug in x equal e, y equal 2, so we have 4 times e to the power 4 minus 1, so 4e cubed for the first one. And the second one, ln e is 1 here. Okay, so we have 2 times e to the power 4. Now we just need to add them together. Okay, so this, so sometimes for the multiple choice question, we just try to confuse you here. Okay, so you just need to make sure we choose the correct answer here. So we have 4e cubed plus 2e to the power 4, the first one. Okay, the first one is the correct answer here. Is that good for question 7? And let's move on to question number 8. Question number 8, we want to find at which point the tangent plane to the surface is horizontal. So if you recall earlier, we write down the tangent plane equation. Let's write that down one more time. The tangent plane is z equal to f of ab plus the partial derivative with respect to x times x minus a plus the partial derivative with respect to y times y minus b. Okay, so this is the equation for the tangent plane. What happens when we have a horizontal tangent plane? Can anyone tell me? Do you remember? If the plane is horizontal, that means it's z equal to a constant, right? Like z equal 2, z equal 3, that's horizontal tangent, horizontal plane, okay? So when we have a z equal constant, what does that mean? Yes, both partial derivative equal to 0. Okay, both partial derivative equal to 0, okay? So we are going to find the partial derivative here. The partial derivative with respect to x, we got 2x plus y minus 1, set that equal to 0. And the other one, take the partial derivative with respect to y, we have 2y plus x plus 4 equal to 0. So we have two equations here. We're going to solve for x and y, okay? So to get the point where we have a horizontal tangent plane, then you just need to say both partial derivative equal to 0 and solve for x and y here, okay? So I guess this is not that bad to solve, okay? This is not that bad to solve at all. So anyone have trouble to solve the equation? You're going to get x equal 2, y equal minus 3, because both of them are linear, so it should be easy. Can I skip the work here for to solve the linear equation?
Yes.
Okay.
Yes, but could you just go over just a little bit more why z is constant again? Because I understand that it's horizontal, but I just don't understand how that like impacts f of x and f of y.
Okay. So you know z equal to a constant is a horizontal plane, right?
Yes.
So that means there's no x variable and y variable. Agree? No x and y.
Yes. Okay.
So if there's no x, there's no y, then the coefficient has to be 0, right? Because we have x minus a here. So in order to get rid of x minus a, the coefficient has to be 0.
Okay.
If it's non-zero, you have something times x, right? Okay.
Right.
But we know we have to, we don't want to have x and y in this case because it's a horizontal plane. Is that good?
Yes. Yeah, I understand it more.
Okay. And can we word this type of question differently? Yes. So for this question, it asks us the point where the point here is just the x and the y value. And I can also ask you, what's the horizontal plane equation? So can you tell me what's the horizontal plane equation?
Z equals some number.
Yeah, so you find the x equal 2, y equal minus 3. So you just plug in, right? If you want to find the horizontal tangent plane, equation, then you just plug in the x value and the y value into the original function, okay? And that will give you a number here, okay? You can do the calculation by plugging x equal 2, y equal minus 3, okay? And this will give us the horizontal tangent plane equation. Is that good? So this is question number 8. Question number 9. We want to use the differential to estimate the amount of metal in an open top rectangular box. Okay, so we have a rectangular box here. Let's say the length, the width, and the height are x, y, and z. Okay, and this is open top, so no top here. Okay, and we know x equal to 12, y equal to 8, z equal to 10, the height. Okay, so we have the x, y, and z value here. And if the metal on the bottom and also in the four sides are 0.1 centimeter thick, so can you tell me what's dx, dy, and dz?
0.1.
0.1, or there's different answer here? Okay, so someone said dx, dy both 0.2. Why 0.2 here? Can you tell me why? So you can see this is x, right? And we need the metal on both sides here, okay? We need the metal on both sides to construct the box. So 0.1 on one side, another 0.1 on this side, so together 0.2. Same thing for the, and this is y, and we need metal on both sides here, so 0.2. How about dz? dz is, because it says no top, so we only need the metal for the bottom here. Okay, we only need the metal for the bottom. Okay, we don't need the top. So that only, we only need to calculate once. So 0.1 here. Okay, only the bottom. Okay, so now we have the x, y, z value, dx, dy, dz, and we know the volume for the rectangular box is x, y, z. So we're going to write down the differential here. V is a function of x, y, z. Okay, so the differential, we're going to take the derivative with respect to x. So we have yz dx. Take the derivative with respect to y, we have xz dy. Take the derivative with respect to z, we have xy dz. So once we have this, we can plug in all the value written down here. Okay, so y is 8, z is 10, dx is 0.2, and x is 12, z is 10, dy is 0.2. The last term, x is 12, y is 8, and dz is 0.1. Okay, so the remaining part here, you just need to do the calculation. Okay, you just need to do some calculation here. The number should not be too bad. Okay, so you can see that's 80 times 0.2, so you're going to get 16, right? Okay, so you just need to add all of them together here. All right, is that good?
Yes, other than like a box and a cone, what other volume equations should we know just in case for the exam if we get like a problem like this?
Okay, so the volume, of course, you need to know the rectangular box. You need to know the cylinder, right? You did something like that on the homework, right? The cylinder. And how about the cone? Do you know the volume for the cone? If the height is h and the top rate and the radius across the top is r, what's the volume?
1/3 pi r squared h.
Okay, so for the cone is 1/3 pi r squared times h, and for the cylinder, you don't need the fraction 1/3 is pi r squared times h. All right, is that good?
Do we have to know surface area too?
Yes, you do need to know the surface area, okay, because this is for the differential. For differential for this one, because it involved the volume here. We're asking the volume, okay? So you don't for this one you don't need the surface area, but when we do the optimization, you do, okay? Because in this module we also talk about the optimization, okay? You do need to know the surface area, okay? So you need to know the surface area for the box, also the cylinder, okay? You don't need to know the surface area for the cone, okay? Is that good?
Can you show the bottom part of your work one more time?
Okay, yeah.
Thank you.
I have a question. Besides the units, how do you know that we're looking at the volume instead of the surface area for this problem?
When they say amount of metal needed, that means the volume here, okay?
Okay, thank you.
And one way to tell is just look at the unit. That would be the easiest way, okay?
Okay.
Okay, so so for anyone have trouble to find the differential here? If you recall, if z is a function of x, y, then we say the differential of f is the partial derivative with respect to x dx, the partial derivative with respect to y dy. So that's when the function of f is a function of 2 variable. Now v is a function of 3 variable, then you have 3 terms here. The partial derivative with respect to x dx, the partial derivative with respect to y dy, the partial derivative with respect to z dz. Okay, that we call the differential. Okay, so this is question number 9. And let's look at question number 10. We want to find the maximum distance from the origin to the curve. Okay, so since it's a curve, so that means this is in 2D here. Okay, if it's a surface, then it's in 3D. Okay, so from the origin to the curve, so we'll say, let's say xy is on the curve here. Okay, and we want to maximize the distance. But usually when we talk about the distance, when we do the optimization for the distance, usually we don't do the distance formula directly because the distance formula involves the square root. So instead of maximize the distance, we want to maximize the distance square. Okay, we want to maximize the distance square. So from the point xy on the curve to the origin, the distance is x squared plus y squared here. Origin, the point is 0, 0. So you just need to set up the distance square formula here. Is that good? And so this is the one we want to maximize, okay? And subject to the constraint, we know the point xy is on the curve, so it satisfies the equation here. So we have 3x squared plus 2xy plus 3y squared equal to 1. So this is how we set it up, okay? So the distance squared is the function we want to maximize here, subject to the constraint. So in this case, we're going to use the Lagrange multiplier here. Okay, we want to use the Lagrange multiplier. So take the derivative with respect to x. We got 2x equal to lambda times 6x plus 2y. Take the derivative with respect to y. We got 2y equal to lambda times. So take the derivative with respect to y here. We got 2x plus 6y. Okay, and now plus the constraint. So this is the system of equation for the Lagrange multiplier here. Is that good? So now we're going to solve for the system equations here. So there's many ways to solve. Okay, so how do you remember how you just solve the equation here? There's many ways to solve. So can you tell me what you do?
I solve for lambda.
You when you solve for lambda, so that means you need to divide, right? 6x plus 2y. And it's not easy to tell if 6 plus 2y equal to 0 or not. Okay, it's not easy to tell. So, okay, someone mentioned multiply the first equation by y, the second equation by x. So we did something like that in class, because doing this, you can see on the right-hand side, we got the exact same thing. So we have 2xy equal to lambda times 6xy plus 2y squared. And the second equation becomes 2xy equal to lambda times 2x squared plus 6xy, right? So now right-hand side, we got the same thing here. So that means the right-hand side also the same. So lambda times 6xy plus 2y squared equal to lambda times 2x squared plus 6xy. Can we divide it by lambda here? Can we divide it by lambda? So let's look at the first two equations. Can lambda be 0? If lambda equals 0, then x equals 0. If lambda equals 0, y equals 0. Okay, so when lambda equals 0, x and y both equal to 0, then it doesn't satisfy the constraint here. Do you see that? Okay, it doesn't satisfy the constraint. Therefore, we know lambda doesn't equal to 0. Okay, so now since we know lambda doesn't equal to 0, we can divide lambda on both sides. Okay, we can divide non-zero number here. So we're going to get 6xy plus 2y squared equal to 2x squared plus 6xy. Now we can subtract 6xy from both sides, and we are going to get x squared equal to y squared, or you say x equal to plus minus y. Is that good so far? Okay, so once we got x equal plus minus y, there's two cases. We're going to plug in both of them into the constraint here. Let's discuss the first case when x equal y. When x equal y, we got 3x squared plus 2x squared plus 3x squared equal to 1. So that gives us, that's 6ax squared equal to 1. So x squared equal to 1/8, right? And x squared equal 1/8, then y squared is also 1/8. Is that good? Because x equal y, so both x squared and y squared, they are equal to 1/8. Now the second case is when x equal to minus y, or you say y equal minus x. Now we're going to plug into the constraint here. We have 3x squared plus 2x, y is minus x. 3 times minus x squared, set that equal to 1. Okay, so we have 3x squared minus 2x squared plus 3x squared equal to 1. So we'll have, that's 6 minus 2, that's 4x squared equal to 1. So x squared equal to 1/4. If x squared equal 1/4, then y squared is also 1/4. So as you can see here, I did not solve for x and y, okay? Because if you solve for x or y here, you're going to get the point, and the plus. You can see you get x equal plus minus 1 over 1/2 here, and then you can get the y value, okay? And the reason I did not solve for x and y here, because anyway, I'm going to plug in here. I need to get the maximum, which is in terms of x squared and y squared. So I really don't care what's the x value. I only care about x squared and the y squared. So you can see here, in the first case, when x equal y, the distance squared is x squared plus y squared. That's 1/8 and 1/4 when you add them together. And the second case, when x equal minus y, the distance squared is 1/4 plus 1/4. That gives us 1/2. Okay, and which number give us the maximum? 1/4 and 1/2. So you can see this is maximum. However, this is distance squared. So what's distance? Can you tell me what's the distance? If distance squared is 1/2, then you just need to take the square root, right? Okay, so that would be 1 over square root 2. Because the question is asking the distance, not distance squared. Okay, so but when we try to do the optimization, it's easier to do the d squared here because it doesn't involve the square root. Okay, it made the question a lot easier. Okay, so the answer we got the maximum here, that's the distance squared. So remember, in order to get the distance, you need to take the square root. For this question, it's asking the maximum distance, which is 1 over square root 2. And if it asking the minimum distance, this is the minimum, then the minimum distance is 1/2. Okay, so this is the minimum distance. This is the maximum distance. Okay, is that good?
So if you can scroll up a little bit, so d squared equals like x squared plus y squared, yeah. So how come the fact that the d is squared doesn't affect your partial derivatives?
Oh, this is just a function f of x, y, right? You don't need that.
Okay, so the fact that the d squared doesn't do anything.
No, no, no. I just tell myself this is distance squared. That's it.
Okay.
Okay. So the function I want to do, the function I want to maximize is x squared plus y squared, which is the distance squared. Okay. I write down this, the distance squared, that will tell me at the end, the maximum I got is the distance squared, not the distance. So that's why I will remember. If you don't write the d squared, I think some of you probably forget to take the square root. Am I right? Okay.
No, yeah, I can see how that happened.
Okay, so that's why I put the distance square here, because I want to remind myself I maximize the distance square, but the question is asking the distance, so I need to take the square root here. Okay,
Okay.
is that clear now?
Yes, the d isn't actually functioning like a variable.
Yeah,
It's just a
in
reminder
fact, we
for
just
you.
want to maximize this function, f of x, y, okay?
Okay. Thank you.
All right, so this is question number 10.
When you were solving for x and y and you had x squared equals y squared, do you still need to account for the possibility of x being negative?
Yes, because as you can see here, I only write it. This question did not ask us the point. Okay, it only asked the distance. So I did not find the x and the y value. So you can see if you want to find the x value and the y value here, you're going to get 1 over 2 root 2, 1 over 2 root 2. And the other one is the -1. So you got 2 solutions from the first case. And you're going to get another 2 solutions here. 1/2, -1/2, -1/2, 1/2. Okay, but I didn't do this part. I just keep the x squared, y squared, because I know my goal is to find the distance. Okay, is that good?
Yes, thank you.
All right.
I have one question. So is the reason why we chose the equation x squared plus y squared, is that because the question asks for distance?
Yeah, the question is asking for the distance. Okay, so if you want to, if you do it this way, maximize the distance, then this is the function you're going to maximize. Okay, but this is not easy to take the partial derivative. When you take the partial derivative, it involves the square root, and the system equation is impossible to solve. So that's why instead of maximize the distance, we maximize the distance square instead. This is the common common thing we do when we do the find the maximize or minimize the distance. Okay, we usually do not maximize the maximize or minimize the distance directly. Instead, we maximize minimize the distance square instead. Okay.
Okay, thank you.
Is that good? All right. Now, question 11. We want to find the point on the surface so that the tangent plane is parallel to the other plane here. So for this surface, we can write this as implicit equation, 6x minus y squared minus z squared equal to 0. So how are you going for the tangent plane? From this equations here, can you find the normal vector? What's the normal vector for the tangent plane?
The gradient.
Yes, the normal vector is the gradient. Okay, so we're going to find the gradient here, which is 6 comma minus 2y comma minus 2z. Is that good? And it says the tangent plane is parallel to this plane, 3x plus 2y minus 2z equal to 1. So for this plane, can you tell me what's the normal vector? What's the normal vector for this plane?
3, 2, -2.
Just the coefficient for x, y, z, right? Okay, and when two planes they are parallel, what's the relation between the two normal vectors? If these two planes they are parallel, then the normal vector are also parallel, right? Okay, so these two normal vector they are parallel here. So that means we can write one vector as a constant scalar multiple of the other one. Agree? Okay, we can write one normal vector as a scalar multiple of the other one. Can you tell me what's the k value? Look at the first component. What's the k value? K equal 2, right? K equal to 2. So now from here, you can solve for y and z, okay? So the second component equal to 4. The third component equal to minus 4. So you can find the y and the z value. Okay, so y equal minus 2 and z equal to 2. Y equal minus 2, z equal to 2. And we want to make sure, because it says no such point exists, so we want to make sure the x coordinate is correct. So how are we going to get the x coordinate? Now we got the y and z value, and the point is on the surface here. So we can plug in the y and z value we got here. So we'll have 6x equal to y squared plus z squared. So that's 4 plus 4, which is 8. So x equal to 8 over 6, or you say 4/3 here. So indeed, the x coordinate is 4/3. So this is the point on the surface so that the tangent plane is parallel to the given plane here. Is that good? Any question about number 11?
Could you guys ask about intersections of surfaces? Or
So this one is asking the point where the tangent plane is parallel to the given plane.
What
And-
if it was orthogonal, Professor?
Okay, if it's orthogonal, if the tangent plane is orthogonal to this plane, then that means these two normal vectors, they are orthogonal, right?
Yeah.
So then what does that mean? You do the dot product here. The dot product equal to 0,
Mm-hmm.
okay?
Okay.
dot product equal to 0. Okay, so if you remember from the homework, we mentioned about the tangent plane is parallel to another plane. And we also mentioned that the tangent plane is parallel, not parallel, is orthogonal to another line. Do you remember? Another line, okay? So for the line, you can find the direction. And for the tangent plane, you can find the gradient vector. So in fact, those two still parallel here. The direction of the line and the gradient, they are still parallel. Do you see that? They are still parallel here. Is that good?
Yeah. Thank you.
And someone is asking here why we multiply by 2, because we say when the two planes they are parallel, the two normal vector they are also parallel. When two vector they are parallel, we can write one vector as a scalar. So I put a k here times another vector. And then we can determine the k value by compare the first component here. So you can see 6 equal to 3k. If 6 equal 3k, that means k equal to 2, right? Is that good? All right, so this is question 11.
Professor,
Yes?
I had a quick question about this one. Why wouldn't
Okay.
the x coordinate be 6 in this case?
Okay, we find the y and z value. It says the point is on the surface here, right?
Mm-hmm.
So that means if the points on the surface, then that means x, y, z need to satisfy this equation. So now we plug in the y value and the z value here to get the x value. So
Okay.
for x, okay?
Okay. Yeah, thank you.
Mhm. Now let's look at question 12. We have the function, and now first it asks us the critical point. So to find the critical point, we need to find the partial derivative here. Take the partial derivative with respect to x. Then we have y cubed times 2x minus 4 times the e function, and set that equal to 0. Take the partial derivative with respect to y, we have 3y squared times the e function. Is that good? And to get the critical point, both of them equal to 0. From the second equation, what do we know from the second equation? Y has to be 0, right? Because we know the e function always positive, never equal to 0. So the only thing can be 0 is 3y squared. So that means y has to be 0. Is that good? So if y equal to 0, the first equation automatically equal to 0. Can you see that? When you plug in y equals 0, so it doesn't matter the x value. It doesn't matter the x value here. The first equation always equal to 0. So in fact, how many critical points do we have? There's infinitely many, okay? So there's infinitely many. And the critical point is in the form x comma 0. Y always equal to 0 on the second equation. And x can be any number, okay? X can be any number. There's infinitely many critical points, okay? Therefore, P is not correct. And now let's look at Q. The extreme value theorem guarantees the maximum value of f on the region D must occur at the boundary point of any closed boundary region. Is that correct? We only need to consider the boundary point? Or there's other candidate we need to consider? Extreme value theorem, it tells us there's two candidates we need to consider. One, the second one is the boundary point, okay? The boundary point. And the first one is the interior point. And the interior point, we just need to consider the where we have the critical point. Okay, so that means Q is not correct. We also need to consider the critical point inside the region. Okay, is that good? And now let's look at R. It says AB is the critical point, and the directional derivative equal to 0 for any unit vector u. Okay, so if a comma b is a critical point for this function here, then we know that the both partial derivative equal to 0, right? The partial derivative with respect to x and the partial derivative with respect to y both equal to 0. Okay, and now the directional derivative, we can use the gradient. We're going to do the gradient, the unit vector. And the gradient, what's the gradient? The gradient is just the partial derivative with respect to x, the partial derivative with respect to y as the two component with the unit vector. And because it's a critical point, so both component equal to 0 here. So in fact, the gradient vector is a 0 vector. 0 vector that with any unit vector, it must be 0. Therefore, the directional derivative equal to 0 for any unit vector in this case, because the gradient vector equal to 0. So R is correct. Okay, R is correct here. Is that good? So this is question 12. And next, we're going to move on to question 13. Question 13, it tells us the temperature given by this formula here based on the location x, y, and which of the following unit vector give us the direction in which the temperature decreases most rapidly at the point 14. So can you, before we do the calculation, can you tell me in which direction the temperature decreases most rapidly? It's in the opposite direction of the gradient vector, right? Okay, in the opposite direction of the gradient vector. When we want to have the, so if it change to increases most rapidly at a given point, then it would be the gradient vector in the direction of the gradient vector. And how about the temperature has no change? The temperature has no change in which direction?
The direction where it's orthogonal to the gradient.
Yeah, orthogonal to the gradient vector. Okay, so you need to know all three of them because you don't know which one you're going to get on the test. Okay, decreases most is in the opposite direction of the gradient vector, increases most in the direction as the gradient, and the temperature has no change in the direction orthogonal to the gradient vector. Okay, now, so it doesn't matter which one, you need to calculate the gradient vector anyway. So we're going to calculate the gradient vector here. Okay, so let's calculate the gradient vector. Okay, the partial derivative with respect to x. So you're going to get minus 600x e to the power negative 3x squared minus y squared. Okay, the partial derivative with respect to y, so minus 2y, so negative 200y times the e function. So this is the gradient vector. Okay, and now we're going to plug in at the point 14. Okay, we're going to plug in at the point 14 here. Okay, so let's plug in. Plug in x equal 1. So you'll get minus 600 e to the power. So that's minus 3 minus 60. Minus 3 minus 16. Right? So minus 19. Am I right? And then plug in y equal to 4. So we have negative 800 e to the power negative 19. Is that good?
Isn't it minus 13? Or am I wrong? The exponent?
The exponent?
Because yeah, even actually, no, never mind.
We plug in x equal 1, so it's
Yeah, I know,
negative 3 minus 16, right?
Yeah, you're right, my bad.
I did the calculation here. Okay, so it should be minus 19. Okay, so in this direction, it gives the temperature increases most. But here we want decreases most, so that means we want to have the opposite direction, right? the opposite direction, that would be 600 e to the power minus 19, 800 e to the power minus 19. Agree? Okay, so this gives us the temperature decreases the most. Okay, the temperature decreases the most in the opposite direction of the gradient vector. Okay, but it is asking the unit vector. The unit vector here. So how are we going to get the unit vector?
Divide by the magnitude.
And what's the magnitude?
Well, the unit vector becomes 3/5, 4/5.
Uh-huh. Okay, so first of all, you can find the magnitude here. 600, 800, you'll get 1,000. Okay, and also you have the exponential e to the power minus 19. So this is the magnitude here. Okay, or yeah, just like some people mentioned, you can scale this down because this vector is in the same direction as 6,8, or you say 3,4. Okay, they are all in the same direction. And in order to find the unit vector, you just need to divide, and this is divided 5, this is divided by 10. Okay, or you can do it directly here. It's just the number is larger. Okay, but you can see you can divide everything by like 200 e to the power minus 19 to get this vector here. Okay, is that good?
So if it just asked for like the, if it didn't ask for the unit vector, then we would just stop after we take the magnitude of the gradient vector?
Okay, if it didn't ask for the unit vector, you can stop right here.
Okay.
Okay.
Thank you.
Any vector pointing the same direction, it gives the temperature decreases most. Okay, as long as pointing the same direction as this one. Okay. So this is question 13. And question 14, we want to find the maximum value of the function subject to the constraint. So this is another one using the Lagrange multiplier. So set up the system equation here. Take the partial derivative with respect to x equal to lambda times 2x. Take the partial derivative with respect to y. Press the constraint. Okay. So here we can solve for x and the y. So when we solve for x and the y, we want to make sure lambda doesn't equal 0. Can lambda be 0? You can see lambda times 2x equal 4. So that means lambda, x, and y, all three of them, none of them equal to 0. Okay. Otherwise, the product, if one of them equals 0, you can see the left-hand side has to be 0. Okay. So now we can divide. X equal to 4 over 2 lambda, or you say 2 over lambda, and y equal to 3 over 2 lambda here. Okay, so since lambda doesn't equal 0, we can do that. And now we have x and y written in terms of lambda. We can plug into the constraint here. So we have 2 over lambda squared plus y squared equal to 1. So we have 4 over lambda squared plus 9 over 4 lambda squared equal to 1. Let's multiply 4 lambda squared on both sides here. So multiply 4 lambda squared, so we're going to get 16 plus 9 equal to 4 lambda squared. Okay, so here we multiply 4 lambda squared on both sides. Okay. So we got 4 lambda squared equal to 25. So lambda squared equal to 25 over 4. Lambda equal to plus minus 5 half. Okay, so now we find the lambda value. Once we find the lambda value, we can put it back here to find the x, y value here. Okay, so the first case when lambda equal to 5 half, then x equal to 2 over lambda. So 2 over lambda. So we'll 2 times the reciprocal of lambda. So that will be 2/5. So we're going to get 4/5 here for x. And y equal to 3 half. times the reciprocal of lambda. The reciprocal of lambda is 2/5. So we have 3/5 here, x and the y value, okay? And the second case is when lambda equal to -5/2, then you're going to get the xy value here. Just the difference is just the sign, okay? And now we want to find the maximum of 4x plus 3y, okay? So we need to plug in the x, y value here. We want to get 4x plus 3y. 4x plus 3y, so that's 16 plus 9, 25. 25 divided by 5, that gives us 5 here. And you can do the same thing for this one. Again, the difference is just the sign. So you're going to get -5 here. So 5 is the maximum and -5 is the minimum. Okay? Is that good? This is question 14. And let's move on to question 15. Consider the rate of change of the given function here. So the rate of change, that means the directional derivative. So we're going to take the gradient here first, okay? Find the gradient of the function. Take the partial derivative with respect to x. So we are going to get cosine x over y. Go inside, take the derivative with respect to x. We have 1 over y. So this is the first component. The second component, take the derivative with respect to y. So we have cosine x over y. Go inside, take the derivative with respect to y. We have negative x over y squared. Is that good? So this is the gradient. Now we are going to consider the gradient at the point pi comma 1. We're going to plug in x equal pi, y equal 1 here. So we are going to get the angle here is pi. Cosine pi is -1, okay? So we are going to get the first component is -1. The second component, this is -1, and that's minus pi over 1. So that gives us pi here. Is that good? So we got the gradient is -1 comma pi. Any questions so far? Let's look at the first one. It tells us the maximum rate of change is square root of 1 plus pi squared. What's the maximum rate of change? Earlier, we talked about the direction the function increases the most is in the direction of the gradient vector. And now the maximum rate of change is the magnitude of the gradient. Okay, so in this case here is square root of -1 squared plus pi squared. So this one is correct here. P is correct. And the second one, it says the function does not change in this direction. Is that correct?
No.
Can you give me the correct direction?
1 pi,
1 pi?
or is it?
Pi comma 1, right?
Oh, that's what I meant. Sorry.
Or opposite direction, okay? But not this one, okay? This one, you can see when you do the dot product, it doesn't equal to 0, okay? The function does not change. You need to, when you do the dot product, we'll have 0 here, okay? So Q is not correct. And there's a unit vector so that the rate of change is phi. So we know the directional derivative at the given point is always between, this is the maximum, and what's the minimum? Maximum rate of change is this number. The
The
minimum,
opposite.
you just need to put the minus sign, right? So the directional derivative is always between these two numbers. And it says there's a unit vector so that the rate of change, which is the directional derivative, equal to phi. Is that possible? Phi is square root 25, right? It's square root 25 between these two numbers. You do know pi is like 3 point something, right? 3 point something squared plus 1 is definitely less than 25. Can you see that? Okay. So it is Is R correct? Phi is way bigger. Okay, phi is bigger than this number here. Okay, so R is not correct. Only P is correct in this case. Only P is correct. Okay. So this is question 15. And let's move on to 16. 16, we want to find the limit here. So to find the limit, we'll plug in X and Y first. When we plug in, we got 0 over 0. 0 over 0. So I think we mentioned something about the, that's back to question number 2. When we have a 0 over 0, remember? When we have a 0 over 0, we mentioned that we're going to see if we can simplify by factoring. If not, if the square root involved, we'll try to do the conjugate. So you can see we cannot simplify. There's no square root involved. And do we have x squared plus y squared? Those two terms involved here, x squared plus y squared? Yes. So in this case, for question 16, we're going to convert to the polar coordinate. Okay, we're going to convert to the polar coordinate here. So we'll have the top is 2r squared, and the denominator is e to the power minus r squared minus 1. Is that good? R squared is polar coordinate, r squared equal to x squared plus y squared. And now when x, y getting close to 0, 0, that means r is getting close to 0. Now when you plug in r equals 0, you have a 0 over 0, but now only one variable involved. What can we do? What can we do? How are we going to evaluate the limit? Yes, so here only one variable, so we can use the L'Hopital's rule here. Take the derivative for the top, you got 4r. Take the derivative for the denominator, you got minus 2r times e to the power minus r squared. Now we can divide it by 2r. Divide it by 2r. So we still have 2 on the top. Now plug in 0. So we have 2 over, there's a minus sign here. Don't forget that. And we have e to the power 0 is 1. So it goes to minus 1 for the denominator. So the limit is minus 2. So this is 16. Okay. So once you convert to the polar coordinate, the whole question become a lot easier here. Okay. So this is question 16. And now let's move on to 17. 17, we have the function has continuous second partial derivative, and x is a function of u and v, y is a function of v. First, we want to find partial z, partial u here, and we want to use the chain rule. Okay, so we're going to draw a tree diagram. Z is a function of xy. X is a function of u and v. Y is a function of v. Now to find partial z, partial u. How many terms do we have for partial z, partial u by looking at this tree diagram? Partial z, partial u. We only have one term, right? So only this one here. So the first one is partial z, partial x. Times this one is partial x, partial u. Is that good? Only one. Okay. And what's partial x, partial u? Look at the function here. X is v squared minus 2u squared. So the partial derivative give us minus 4u. So we're going to get minus 4u times partial z, partial x. Okay. So we done the first part here. Negative 4u times partial z, partial x, and there's no partial z, partial y here, so we just put 0, okay? And the second one, we want to find the second partial derivative. So to find the second partial derivative, we use the first one, and we're going to take the derivative with respect to u on both sides, okay? We're going to take the, in order to get the second partial derivative with respect to u here, we're going to take the derivative with respect to u one more time, okay? So on the left-hand side, you'll have the second partial derivative with respect to u. On the right-hand side, to take the derivative with respect to u here, you can see it's the product of two functions. So we need to use the product rule here. Okay, we'll use the product rule here. Take the derivative for the first factor with respect to u, we got -4 times partial z partial x plus the partial derivative with respect to u for this second factor here. So this part here is the product rule. We take the derivative for the first factor and we take the derivative for the second factor, product rule. Now, what's this? Because you can see we want to write this in terms of partial z, partial y, partial z, partial x, and also the mixed partial derivative here with respect to x or y. So we don't have this here. So we need to simplify this. So we are going to use the same tree diagram, but now we are going to take the derivative for partial z, partial x. So we are going to put partial z, partial x on the top here, okay? We're going to take the derivative for partial z, partial x, and we know partial z, partial x still a function of x, y. X is still a function of u and v, y is a function of v. So we're going to use the same tree diagram, but now we're going to change the parent function on the top as partial z, partial x, because now we are taking the derivative for this function, okay? So again, we only have one term here, okay? So using this tree diagram, we can write as so let's write that. So for this one, we're going to use this function, take the derivative with respect to x. So we have this. Use the parent function, take the derivative with respect to x, and then partial x, partial u. We only have one term, okay? And what's partial x, partial u? We did that earlier. Partial x, partial u is -4u. This is -4u, okay? So now we can combine them together, simplify a little bit further. We have -4u times -4u that gives us positive 16u squared. And what's this? This is just the second partial derivative with respect to x twice, right? So now we have find the answer. The second partial derivative with respect to u equal to -4 times partial z partial x plus 16u squared times the second partial derivative with respect to x. Okay, so we have -4 and 0, and that's 16u squared. And the other two, we don't have that. Okay, so we just put the 0 here. Okay, so that's the final answer. Okay. Is that good for 17? So if you recall, I did the fall 2019 exam the other day. I think there's one question very similar to this one. Do you remember? Do you remember? On that test, the fall 2019 exam, there's one question very similar to this one. Okay. So this is question 17. And let's move on to question 18.
Can you,
yes?
Can you go back to 17?
Yes, which part?
Can you explain the dz dx partial z partial x that you circled right there? And
this one?
The one under that one. Can you explain it?
Okay. So here, this whole thing, are you okay with the product rule we did here?
Yeah.
Okay. So now we need to simplify this. For the second term here, we want to use the function partial z partial x. We want to take the derivative with respect to u, right? This is the function, and we want to take the derivative with respect to u.
Okay.
Therefore, we put the top function as partial z partial x here on the top. And we'll want to find the function, what's the, when we take the derivative with respect to u, then we need to draw the tree diagram, okay? And this is the tree diagram with respect to u, that's the only term involved. So that's why we have this. the first term here is take the derivative with respect to x, and then partial x, partial u. This is how we write down the using the tree diagram to write down the formula for chain rule, right?
Okay, I understand now. Thank you.
All right. And let's move on to question 18. Question 18, it gives us the contour map, and we want to determine the sign for the partial derivative. So the first one is the partial derivative with respect to x at the point A. So when we take the partial derivative with respect to x, which variable we are holding as a constant, x or y? Do you remember?
Y is held constant.
Yeah, we hold y is a constant. So that means the y value is fixed, right? The y value is fixed. So in this case, you're going to draw a horizontal line here. So you can see on the horizontal line, the y value is fixed. Agree? So when we increases the x value, then you can see the contour map here. The at the point A, this is 30, and increase to like 40, 50. Did you see that? The function value increases. When x value increases, the function value increases, then the partial derivative is greater than 0. Is that good? For the point B, we want to find partial f, partial y. So in this case, x value is fixed. When the x value is fixed, we're going to draw a vertical line. Excuse me. We'll draw a vertical line, and you can see on this vertical line, the x value is holding as a constant. So now when the y value, now let's increase the y value a little bit, and you can see the contour map here. This is 20 and 30, 40. Can you see that? When the y value increases, the function value also increases. So again, this is greater than 0. Partial f, partial y is greater than 0. Now the last one, partial f, partial x at the point C. So now again, we want to hold y as a constant. So you're going to draw a horizontal line here at the point C. So when x increases, so you can see at the point C, the function value is -10. And when the x value increases, the next one here is -20, 30. So the function value decreases. Can you see that? When x value increases, the function value decreases here. So the derivative is less than 0. Okay. Is that good?
Yeah, so I had a question. So would it only ever be equal to 0 if the contour lines around it were parallel?
Parallel. If it equal to 0, then that means when you increases, yeah, you won't see the changes. Okay, so that means, like, for example, if partial f, partial x at the point A equal to 0, then that means when you increases, when you draw the horizontal line here, and the label curve is just along the horizontal line here, so it doesn't change at all, then you will be equal to 0. You see that? Okay.
Yeah, thank you.
All right, so this is question 18. And let's look at 19. 2 more questions, okay? Question 19, given the function, first, how many critical points does the function have? So we need to find the critical point by taking the partial derivative. The partial derivative with respect to x, we have 6xy minus 6x, set that equal to 0. The partial derivative with respect to y, we have 3x squared plus 3y squared minus 6y equal to 0. Okay, So this is from the first partial derivative. Now, from the first equation, we can take out 6x. So that means x equals 0 or y equal 1. Is that good? And if x equals 0, we're going to plug in x equals 0 here. We'll get 3y squared minus 6y equal to 0. So y equals 0 or 2. So in this case, we got two critical points, 0, 0, and 0, 2. Is that good? And there's another case when y equals to 1. When y equals to 1, we have 3x squared, 1, so plus 3 minus 6 equal to 0. So that means 3x squared equal to 3, so x equal to plus minus 1. So in this case, we got another two critical points. Y is 1 and x equal plus minus 1. So 1 comma 1, negative 1 comma 1. So there's total 4 critical points. Is that good? So there's total 4 critical points here. 4 of them, those 4. Okay. Once we find the critical points, as you can see, given 2 points P and Q. P is negative 1 comma 1. That's a critical point. Q is 0 comma 0. That's another critical point. Okay. So both of them are critical points, and we want to check. We want to classify the critical point using the second derivative test. So the second derivative test, we need to find the second derivative. Okay, so take the derivative one more time with respect to x. So we got 6y minus 6. The second partial derivative with respect to y. So we're going to get 6y minus 6. The mixed partial derivative. From here, we take the derivative with respect to y. We got 6x. Okay. And the second derivative test, we need to calculate the discriminant. Okay, so this is the discriminant minus the mixed partial derivative square. Let's look at the first point P. The point P is minus 1 comma 1. So when we plug in x equal minus 1, y equal 1, we have 0 times 0 minus negative 6 squared. So as you can see, we have 0 minus 36. This is less than 0. So what do we have at the point P? Yes. So this is a saddle point here. Okay. Point P is a saddle
I
point.
knew she was doing this.
And point Q is 0 comma 0. Plug in 0, 0, we have negative 6 times negative 6 minus 0 squared. And this time we got a positive sign here. If it's a positive sign, you need to look at the second partial derivative with respect to x. This is less than 0. So what do we have? Local
Max.
Local max. Okay, we have a local max here. Okay, and so if I give you another point, let's say R. If I say R is the point 1 comma minus 1. So what do we have at R? Do we use the discriminant here?
I don't think we have a critical point there.
Okay, so yes, you can see we have 4 critical points. Okay, so sometimes we try to trick you. Okay, we give you a point that's not a critical point at all. Okay, so you need to say this is not a critical point. Okay, so you need to make sure the point we have here given here is a critical point. If not, then we don't even use the second derivative test. You just said it's not a critical point. Okay, so this is question 19. And next, the last one, question 20. And we don't have many students get the question correctly here, but I can tell you we always have similar type of question like this, so you make sure you know how to do it. Okay, we want to find the extrema of the function on the region R, and the region R is half of the disk. So in this case, can we use the, so of course you need to consider the interior and also the boundary. For the boundary, before we do the question, I just want to ask you, for the boundary, can we use the Lagrange multipliers? Why not? Why not? The answer is no, but why not?
My circle, but we have the little horizontal line.
Okay. In order to use the Lagrange multiplier, we need to write the boundary as one equation. Are we able to write the entire boundary as one equation?
No.
No, right? It's two separate equations here. One is the line segment, the other one is the half circle, okay? So in this case, we cannot use the Lagrange multiplier, okay? So let's do this question here. Let's start with the interior. For the interior, you're going to consider the critical point, take the partial derivative with respect to x, take the partial derivative with respect to y. So we're going to get 2x minus 2 and 4y. So you're going to get the critical point, which is 1, 0 here. Is 1, 0 in the interior?
Yes.
Yes, 1, 0 is in the interior here, okay? So that's the candidate. And now we're going to consider the boundary. The boundary consists of two curves. One is the straight line, the line segment, and the other one is half the circle, okay? So we're going to look at C1 first. C1, can you write the equation for C1? For C1, the x value is always equal to 0, right? And can you tell me the bounds for y? It's from -2 to 2. Okay, now on the boundary, the function, I'm going to replace x with 0 here, okay? So the function can be written as 2y squared, okay? When you're plugging x equals 0, you got 2y squared, okay? So you can find the derivative that gives us the critical point y equals 0, okay? So I'm going to set up the table here. We got the critical point, and we also get the at the boundary, we have y equals 0. We have y equal to plus minus 2. So this is for the curve C1. We have 3 points to consider. Y equals 0 is the critical point, and 2 endpoints, y equal plus minus 2. Okay. We can figure out the x value if you want to later. Okay, C2. C2 is the circle, half of n, x squared plus y squared equal to 4. So we can replace y squared with 4 minus x squared here. Y squared equal to 4 minus x squared. So you can see we're going to replace the y squared, the last term, with x squared minus 4. Therefore, the function can be written as x squared minus 2x plus 2y squared. 2 times y squared is 4 minus x squared. Simplify this, we're going to get minus x squared minus 2x plus 8. And now the x value, look at the graph here. For the semicircle, x value, what's the smallest x value? What's the largest x value? X is from 0 to 2, right? From 0 to 2. So x is from 0 to 2. Now take the derivative to find the critical point. And we got x equal to minus 1. So we got a critical point x equal minus 1. However, x equal minus 1 is not in the interval here, right? Can you see that? X equal minus 1 is not inside the interval. So we don't consider this critical point because it's not between 0 and 2. Okay, so now for the curve C2, we only need to consider 2 endpoints, x equals 0, y equal to, x equals 0 and x equal to 2. Okay. And now we're going to figure out the function value. The function is x squared minus 2x plus 2y squared. Having 1 comma 0, we got 1 minus 2 plus 0. That gives us -1. On the boundary C1, this line segment here, we got the y value is 0 to -2. Those are the 3 candidates we have here. And also we know the x value is always 0. On the boundary C1, we know x value is all 0 here. Now plug in, we have a 0 minus 0 plus 0. 0 minus 0 plus 8. 0 minus 0, that's also 8. Okay, and now at the curve C2, we only need to consider 0 and 2 here. When x equals 0, because it's on the circle, the boundary is C2 is the half circle. So when x equals 0, y equal to plus minus 2. And when x equal 2, y equal to 0. Okay, but you can see this point is duplicate from here, so we don't need to consider the function value. We already got that already, but this one never happened before, so we are going to calculate the function value here. So plugging x equal 2, y equals 0, we have 4 minus 4 plus 0, so that gives us 0 here. So there's 5 function value we got here. So you can see that the largest number is the max. So this is the max. The maximum occur at the point x equals 0, y equal to plus minus 2. And the minimum is at the critical point. This is the mean. The minimum is at the critical point 1 comma 0. Is that good? So now we have finished the review. This is the last question. Okay.
I have one question about this question.
Yes.
So on the picture, how does this look graphically where the min and max are? Because I got this wrong because I put the min and max for 2 and -2 because I should have known it was a trick question. That'd be too easy. But so like 8 and -1, where does that show up on this graph? Or like, what does this like mean graphically? Yeah.
Okay, we don't see from this graph here because we find the max and mean for this function. This is the function we want to find the max and mean on this region. So the xy is from this region here.
Got it. Okay, that makes sense.
So this is the domain of the function we consider here. So if this is the domain we consider, where we want to find the maximum and minimum of the function. Does that make sense?
Yeah, okay, that makes a lot of sense. Thank you, Professor.
Okay. All good now? Okay, let me start recording.